Okay, sorry for all the waiting and double clicks. I just had to make sure the live stream is working properly. Okay, now we can start recording. And welcome everyone to our pre-sec ML, so privacy security ML seminar series. Today, I'm really pleased and excited to have Florian Tramer that is going to give a great talk. So I'll just go through the abstract, and I'm quite interested in every single bit, like, not just the average case, the worst case, the connection between the two, and also how this is going to be helping to audit correctness of differential privacy defenses. So Florian is currently a visiting researcher at Google Brain, and is an assistant professor of computer science at ETH Zurich, which I believe we were just chit-chatting a little bit earlier. So it's going to be officially starting in August. Florian's research interests lie in computer security, cryptography, and machine learning security. And in his current work, he studies the worst-case behavior of deep learning systems from an adversarial perspective to understand and mitigate long-term threat to the safety and privacy of users. I love it so much, and this is confirmation bias. I kind of, work in similar areas, and it's all just confirmation bias, but not. It's just, a great topic, and Florian is also a great speaker. So I'm really looking forward to the talk. Thanks once again, Florian, for accepting our invitation, and the stage is all yours.
Yeah, thanks a lot for the invite and for the very nice introduction. So yeah, let's get started. So as the title of my talk suggests, we're going to talk about privacy leakage in neural networks. I'll be discussing sort of various ways in which we could measure privacy leakage in neural networks from sort of either an average case or worst case perspective, and how we could also have attacks that either target sort of the average user or kind of the worst case user in a data set. So hopefully this will make a bit more sense as we get along, but then let's just get into it. What we'll talk about today are basically neural networks. I mean, nothing I'm going to say is particularly focused specifically on how neural networks operate, so we're not going to go really into detail here. Just for the purpose of this talk, you can think that there's some data set, some training set that is maybe privacy sensitive, that's collected from various users. And from this, we're going to train some machine learning model basically by minimizing some kind of loss over this training set. And then later this model can be used on other data that comes from a similar distribution. So the model sort of generalizes from its training set to new data. And the problem we're going to be concerned with here, the privacy problem, is that these trained models, if you're not careful, they tend to leak parts of the training set. And there's sort of been a variety of examples of this happening over the past few years. So this example here at the top left is actually something that happened with the real Google Translate service, where there was like some random garbage you could feed it. And if you asked it to translate from like Somali to English, it would suddenly start spitting out like biblical verses that it had just memorized from its training data. And in some work that I did with a whole bunch of other folks 2 years ago, we sort of went and looked into how these kind of leakages work in new language models, so things like GPT-2 from OpenAI. And we found that there also, you could sometimes just randomly prompt this model to generate text, and it would just spit out like things it had memorized from its training set. So in this specific case here, it just spit out like the sort of contact information from someone that it found online. So an email address, a phone number, a fax number, etc. And this isn't just for text. There's also been examples of people have shown that something like this could happen with models trained on images, where you might have a model trained for something like facial recognition that would somehow learn the basically you could, as an adversary, then extract features of someone's face that would sort of be recognizable. And so these are the kind of leakages that we care about here. To make things a bit more specific, what this talk is going to be about is one specific privacy leakage and attack on machine learning models, which we call membership inference attacks. And this is a very, very simple attack setup, and that's also one of the reasons why it's kind of nice to study. where basically we're going to have a model that's trained on some training set that the adversary doesn't know about. And the goal of the adversary will be sort of given some data point. The adversary has to guess whether this particular data point was actually in the training set of this model or not. And so the attacker sort of has to interact with the trained model in a way to sort of figure out whether this specific example was used to train the model or not. So this is a very simple attack scenario. You could sort of ask, well, why should we care about membership inference per se? And there's kind of multiple reasons why these attacks are interesting to study. On the first part, well, maybe this is actually an attack, like a real attack, a real privacy leakage that you could be concerned about. And sort of examples of this could be something like a model that's been trained on some very sensitive medical data, where sort of just the fact that you were part of the training set might sort of be correlated with some bad medical condition or something like this. Sort of beyond these kind of maybe a little bit esoteric situations, membership inference is also just interesting because it's often used as an attack component for things like data extractions. For example, this attack I showed at the beginning where we managed to get training data out of GPT-2, internally this attack uses something like a membership inference attack. And then finally, one reason why these attacks are also very interesting is because of their simplicity. They can give us a sort of nice formal upper bound on data leakage. In that, what I mean by this is essentially if membership inference doesn't work, then you can be sort of fairly confident that no other type of privacy leakage, or sort of there's a general class of privacy leakages that are not going to be possible. And so in that sense, it's kind of a nice class of attacks to consider if you're sort of trying to figure out whether your model might be vulnerable to more complicated attacks. For those here who like cryptography, I would suggest this sort of the following analogy with what we do in cryptography is that when we study the security of, say, an encryption system, we typically also consider sort of very simple and formal attack models, so something like a chosen plain text attack, which in itself isn't really an interesting attack because it's kind of like the adversary already knows the plain text to begin with. And so it's really like an attack that we use kind of as part of an analysis where we sort of know that if you can do something like a chosen plain text attack on an encryption system, there's probably worse things you can do down the road. And if we can show that chosen plain text attacks are impossible, then we sort of have very good reasons to believe that sort of sometimes we can even prove that a whole class of sort of broader attacks aren't possible. And so I think membership inference attacks are kind of to privacy what these attacks are in the context of encryption systems. And that this is kind of the way I tend to think of it. So what we'll talk about today is I'm actually going to reviewing sort of the way in which membership inference attacks are designed and evaluated so far, and argue and hopefully convince you that this is actually flawed in a number of ways. And there's sort of the way we evaluate these attacks should be slightly different than what we've been doing so far. And then I'll present a new attack that we developed with some colleagues at Google that sort of takes a very principled approach to exactly doing what we think a membership inference attack should actually succeed at. And as we'll see, this attack will work extremely well against outliers in the data distribution. And then after that, we'll consider an even stronger attack, sort of a slightly different threat model that then will actually work for any input in your training set. And so this is in one way how we're sort of going to go from worst case to average case leakage. And then finally, we'll talk about defenses and how we can use these ideas and these attacks to audit them. Okay, so let's jump right into it. And what we'll talk about first is basically the simplest possible, or one of the simplest possible membership inference attacks. A membership inference attack that comes up very often in the literature as sort of a baseline that people might try to improve upon. So remember that when we train a machine learning model, what we're essentially doing is telling the model to minimize some loss on the training set. So kind of what we'll expect to happen is that on examples that the model was trained on, the loss is going to be very, very low. And this is kind of on this plot is just sort of a histogram of the loss values, kind of scaled just so they look a bit more, the distributions look a bit prettier, of, on the one hand, examples that were actually in the training set, we're going to call these members, and then other examples that were actually not in the training set in red. And as you see, this distribution is actually shifted a bit to the right. And so actually, on average, it is true that the model has lower loss on members than on non-members. And so the way in which we can now try to do membership inference is to just set some decision threshold somewhere and just say that sort of, if we observe an input where the loss is lower than this decision threshold, we're going to say, well, this is probably a member. And you can sort of try to set this decision threshold at different areas on sort of different values of the loss. And then finally, what you get from this is you can sort of plot just a standard ROC curve, where here basically for every place where you could place this, this threshold on the loss, you can compute two metrics. One is your false positive rate, which is essentially how often do you guess that something is a member when it actually isn't, so you kind of make a mistake. And then contrast this with your true positive rate, your recall. So kind of how many times do you actually correctly infer membership. And this sort of line, the straight line in the middle is kind of the trivial thing you can do. If you just sort of guess randomly, you're going to have false positive rate and true positive rate that are completely equal. And sort of an attack that does better than just random guessing should hopefully be above this line somewhat. And it turns out that this very simple loss thresholding attack is above this line. So the area under the curve here is about 59%. So it sort of achieves performance that is better than random guessing. Its sort of accuracy is about 61%. And this is kind of how membership inference attacks have been evaluated so far in most of the literature. The problem with this is that these are all kind of average case metrics. Kind of what this tells you is that sort of on average, the losses of members and non-members are indeed different. We saw that in the previous slide when we sort of looked at the full distributions. And so on average, the attack will be able to kind of distinguish members from non-members with sort of better than chance probability. The issue is that sort of average case leakage is a very poor metric for privacy, because it doesn't really tell you anything about whether the attack actually manages to infer membership of say, specific individuals. It just sort of tells you, on average, across the entire population of users, there's sort of some information that's leaked. Sort of as an analogy, you could consider, say, I don't know, say you're trying to guess people's social security numbers. You could have an attack that manages sort of on average to guess one digit of each person's social security number. And that's not a particularly concerning privacy attack, because kind of, well, on average, it's just, okay, you learn one digit of every individual, but that's not really very useful. An attack that only works for, say, 1% of users, but for those 1% of users, it recovers the whole social security number, would be a much, much stronger privacy attack, but sort of on average, it actually leaks a lot less information. It turns out that these membership inference attacks, they exactly have this problem, is that if you consider how well they work for sort of in the worst case, so if you consider this area here on the plot, this is where we have a very low false positive rate. So this is basically the area where the attack is very, very confident. It makes essentially no mistakes. But as we can see, it also makes no correct predictions in this regime. Basically, if you're trying to have an attack that's very confident, that can sort of tell you very precisely if someone is a member or not, this kind of attack will not enable you to do this at all. And so even though the sort of average leakage is above 50%, the attack essentially will never allow you to tell with confidence that that some data point was a member of the training set or not. To kind of make this even more explicit, the way we kind of advocate for looking at these results is that instead of plotting an ROC curve, you should just plot your ROC curve in log-log scale. And this kind of enforces looking at what happens at sort of very low false positive rates and sort of regimes where your attack makes very, very few mistakes. And so here you can see that this sort of simple loss thresholding attack doesn't really work at all. In this regime, it does no better than chance. And so that's not really great, because this just means this attack really doesn't work. And in a way, from a privacy perspective, I don't think we should be particularly concerned about attacks like this. And it also means we probably shouldn't evaluate attacks in the way they've been evaluated so far with these kind of average case metrics, because it doesn't really tell us whether the attack works or not. In particular, it turns out that not all attacks are this bad. So for example, there was an attack that some people at Facebook published about 3 years ago. This is from Alex Sablerol and co-authors. And if you look at sort of the average case performance of this attack, like its accuracy or its ROC, they're actually worse even than this sort of very simple attack we just looked at. But it turns out this attack does like 100 times better if you consider very low false positive rates. And so this attack here, the second attack, I would argue is a much, much stronger attack on privacy, because it turns out that it can actually tell you with very high confidence that some members of the training set were members. Like there's a small fraction of the training set where the attack very confidently reaches the right decision. And this is much, much more problematic from a privacy point of view, even though sort of on average, it doesn't do very well. And so what we're going to see now is how to do sort of even better than this attack by essentially following kind of the same ideas, but really being focused on like this is the way we want to evaluate the attack. We want the attack to work sort of very low false positives. So first of all, we have to kind of understand why this original attack, this sort of loss thresholding attack, doesn't work. And the insight here is essentially that not all training examples are equally hard to learn. And so kind of applying a single threshold to the losses of examples is kind of a bad thing to do. So here's just an illustrative example. Consider this image of a cat, which is sort of a very, very canonical image of a cat. The model tells you it's like 90% confidence this is a cat. Here I'm just using confidence instead of loss. You can sort of think of these interchangeably. So yeah, you show this image to a model. The model tells you 90% confidence, I think this is a cat. Then you show it this image on the right, which is sort of an extremely blurry and sort of slightly out of distribution, maybe picture of a truck. And the model tells you, okay, I'm like somewhat 85% confident this is a truck. And I would argue that even though the confidence of the model on this truck image is lower than on the cat image, it's probably much more likely that this truck was in the training set. Because in some sense, the fact that the model is even confident at all on this picture is kind of surprising and unusual, and probably hints at the fact that it saw this specific image during training. To make this even more concrete, what we can actually do here is just explicitly look at how different models, some that were trained on a specific image or that were not trained on this specific image, what kind of confidence or loss they would assign to this image. And if you do this for an image like this cat on the left, so again, what we do here is we just train, I don't know, a few hundred models on some data set where like some of the models will be trained on this image of a cat and some of them will not be trained on this image of a cat. And then we just ask these models like, what's your loss on this image? And now for the specific cat image, what you're essentially going to see is that the two distributions are going to be essentially the same, because it doesn't really matter whether the model saw this specific image of a cat to know that this is a cat. For images like this truck, however, whether a model saw this specific image or not makes a huge difference in its loss. And in particular, the distributions you get on losses when the image is a member versus not are going to be much, much easier to distinguish. But here also you see that it's basically going to be a bit hopeless to run an attack with a single threshold like we were doing originally, because the distributions you get for this truck image are going to be very easy to separate. You can sort of nicely place a threshold in between these two distributions and sort of say, if I see a loss that's lower than this threshold, I'm like very, very confident it's a member. But if you use the exact same threshold on the loss for this cat image, you'd essentially be randomly guessing because the loss is always going to be lower than this threshold. And so this basically shows why this kind of simple approach where you just threshold the loss of all examples kind of indiscriminately just doesn't work and essentially reduces to always randomly guessing. So now that we have kind of this insight into how losses behave and how there's sort of some examples that are going to be harder than others, we can move on to designing an actual sort of strong membership inference attack. And the way we're going to do this is to really sort of maybe rethink a bit the problem from first principles. So the way we design this attack, sort of in the first stage, right, what do you get to observe? You have some model to call F here, you have some input X. You can query this model and get a loss. This is the quantity that you observe. What you're actually, the answer you're trying to get is basically, is it more likely that I have observed this loss in a world where this example was a member of the training set versus the sort of alternative world where it wasn't? And this quantity, sort of this ratio of these two probabilities is a sort of well-known quantity in statistics. Is called a likelihood ratio. And it turns out there's like sort of very formal statistical theorems that will basically tell you that this is the right quantity you should be computing and thresholding on if you want sort of the best possible attack at a specific false positive rate. And so since we want an attack that works at sort of very low false positive rates, what kind of statistics tells us is what we should do is compute this specific likelihood ratio and then just place the threshold on this likelihood ratio so as to get sort of a very low false positive rate. So this is what we're going to do. Now, the issue is that we need to somehow compute or at least approximate this ratio of probabilities. Like, what's the probability we would have observed this loss if the example, the target example we have was actually a member or not? Well, we can just go and like try to empirically estimate these probabilities. And this is exactly what our attack does. So the first step in the attack is essentially we're going to train what's called a shadow model. So this is something that a bunch of prior membership inference attacks have done as well. We do it here in a slightly different way that's kind of inspired by this previous attack from Sablerol and his co-authors at Facebook that we found to work very well. So what we're going to do here is we're basically just going to sample some data set that's sort of from the same distribution as the one that the original model we're targeting was trained on. And then we're just going to train two models, one with the target example we care about and one without it. And we're going to repeat this process a number of times. And so we're going to have a collection of models where the input was a member and a collection of models where the input was not a member. And then we can just, for each of these models, compute their loss on the input we care about. And so this way, we're sort of going to empirically approximate these distributions. And then sort of the last step of our attack, which is actually, it's sort of a very simple step, but it turns out is very, very important to get good performance, is that we're not just going to treat these distributions as kind of just empirical histograms or whatever. We're actually going to make sure that we can model these as sort of a nice parametric distribution, in this case, Gaussians. And so we're going to sort of scale these losses so that the distributions look approximately like Gaussians. We're going to fit a Gaussian distribution to these losses just by sort of empirically measuring the mean and standard deviation. And then we're going to compute the probability of this observed loss under the assumption that losses follow a Gaussian distribution. And so, well, how well does this work? So this is how well our attack works on a sort of a well-generalized model on CIFAR 10. Again, what's actually kind of interesting is that if you look at the attack performance sort of on average, if you just look at the sort of balanced accuracy of our attack, it's like slightly better than the original sort of baseline attack we started with, but not like noticeably so. And so again, this is just, I think, not the right way to evaluate whether a membership attack works or not. But if we look at sort of how the attack performs at low false positive rates, it's doing much, much better. It's doing like 1,000 times better than the baseline attack, and maybe like 10 times better than this attack from Sablerol, which is actually a somewhat similar attack to the one I just presented on the previous slide, but there's sort of a number of kind of trivially sounding, but actually very important differences in how we set up our attack. And if you're interested in these, I invite you to take a look at the paper. It turns out that this sort of fitting of Gaussian distributions to the losses that we observe is very important. And then there's sort of steps you have to take to make sure everything you do is kind of numerically stable. And then we show that we can get even better results if you don't query the model just once, but sort of multiple times on slightly different versions of the input, and sort of all kind of little tricks that none of which are necessarily new. There's sort of other membership inference papers in the past that have done similar things. But our point here is kind of that if you combine all of these things in sort of the right way, you can, and then evaluate the attack in the right way, you actually get something that's like much, much better than what we had before. So this is basically to set up the evaluation framework. I think is the right one for membership inference attacks. I think we should evaluate these attacks, the performance of these attacks at sort of low false positive rates, and sort of a regime where the attack can confidently infer membership for like some subset of examples. It's a very small subset of examples, right? If you look at the true positive rate, like the recall here of the attack, it's like somewhere around 1%. So there's maybe like a 1% of the examples where the attack can very, very confidently say this is a member. But this is a privacy issue, right? This means that if you happen to be one of those 1%ers, well, then that sucks for your privacy. But so now we have this attack, but it only works for this 1% maybe of users. And so what we're going to look at next is if we can somehow find a way to get an even stronger attack that gets sort of an even higher recall at low false positive rates. So first, let's maybe understand like where our attack works and where it doesn't. Well, basically, if we come back to these distributions we looked at before for, say, this truck, which is a clear outlier, the loss distributions are very, very distinct. Sort of whether the input was a member or not gives you extremely different loss distributions. And so for examples like this one, inferring membership confidently is quite easy. And it turns out that for these kind of examples that are clear outliers, the attack works incredibly well. And then there's other examples like this cat that are clear inliers, that are sort of very canonical representatives of their class, where the loss distributions are essentially identical, and there's really no hope to infer membership here. And so the attack if you limit the attack only to these specific examples, it actually does essentially no better than chance, because it just cannot separate these distributions. If you observe some value, there's no way to tell whether it came from a case where the model was trained on an example or not. And yet, now I'm going to present a new attack that actually also works on these inliers. And so here we're essentially going to show an attack that on average across the entire training distribution is going to do nearly as well as for the sort of worst case outliers. So in particular, if you look at this plot here, for the outliers in blue, our new attack is essentially going to do just as well, if like a tiny bit better than our previous attack. In a sense, there's not like you can't really do much better for these outliers because they're already like very, very easy to distinguish whether they're members or not. But for the inliers, like this cat image, our new attack is going to do like orders of magnitude better. It's basically going to go from an attack that has like near chance performance to one that performs nearly as well as our previous attack on outliers did. So how do we do this? For this, we're going to introduce a new threat model, sort of a new attack model, which we call privacy poisoning. This is something we looked at in a very recent paper we put out. This is a collaboration with a bunch of people. And the idea here is that now we're going to give the adversary a slightly sort of a slightly new capacity or a different capacity than before. The adversary is going to be allowed to poison the training set. So by this, we mean that the adversary sort of participates in the training data collection. Maybe the adversary is one of the users who contributes data. And the adversary will just be able to pick their share of the data however they want. But after that, they don't interact with the model training anymore at all. So this is kind of different than previous works that have looked at sort of privacy attacks in federated learning or decentralized learning or so on. Here, the adversary really, all they're allowed to do is just pick their share of the training data in any way they want. And then after that, they get to interact with the model and launch privacy attacks. And basically the reason why this capability of the adversary to poison the data helps a lot, sort of the insight behind our attack, is that poisoning can actually transform data inliers into outliers. So let me try to illustrate here this kind of a very simple example of how such an attack can operate. So consider again our very canonical cat image, which is represented here in sort of the space of cat images that the model is trained on. Essentially, whether the model is not trained on this specific cat here in the middle, or it is trained on this specific cat, like the loss distributions you get are essentially the same. And so this is kind of a setting we were previously where just membership inference is kind of impossible. What you can now do with poisoning is essentially just make sure that you're going to have a whole bunch of images sort of around the cat image that you're targeting, which are, say, mislabeled. So they're very much out of distribution. So the model is basically going to believe that these images should be dogs. So this is kind of the poisoning attack here. And so now all of a sudden, the model's behavior on the specific cat image is going to be very different, because when the image is not there, the model is going to believe this should be a dog, and so it's going to have a very high loss. And when the image is there, it's going to sort of be, oh, okay, this should actually be a cat. And so it's going to carve out sort of part of its decision boundary for this image. And so now, because of this poisoning, we've sort of gotten into a situation where we've kind of made the distributions, the loss distributions, a lot easier to separate. And this is kind of the principle behind these privacy poisoning attacks. It turns out that you can use a principle like this for a lot more than just membership inference. So in our paper, we show that you can use attacks of this kind to boost membership inference by like a couple of orders of magnitude. And crucially, this only requires poisoning like a very, very small fraction of the training set. So to target any specific image that you think might have been in the training set, the adversary only has to poison something like 0.1% of the entire training set, or even less. And we also show that you can do attribute inference in this way. So this is a slightly different setting where, say, I know many things about you, like most attributes about you, but there's maybe some sensitive attribute of your data that I don't know about and I'm trying to infer. And we show that you can do attacks of this type with much better success rates if you can do poisoning. Here also we sort of evaluate things at sort of low false positive rates and show that you can do much better than prior work in this setting. And then finally, we consider also a data extraction setting where we take a text data set. So this is a model that's trained on sort of a subset of Wikipedia, and where there's, in some places in the data set, there's going to be secret canaries inserted. So these are sort of 6-digit numbers that we just insert in random places in the training set, and the goal of the adversary is to recover these random numbers. And we show here as well that if you can poison the data set by just adding a very small amount of malicious data to the training set, you can recover these secrets much better than if you weren't poisoning the training set. And so now we've seen an attack where essentially we're no longer limited to just targeting outliers, where it's sort of easy to tell whether they're a member or not. Via poisoning, we can sort of make sure that any point we want, it sort of looks like an outlier. And so even if your data happens to be sort of the most canonical data in the world, you might still have to worry about privacy leakage if there's an attacker out there that sort of tries to target you and sort of makes sure that your data sort of looks weird to the model via poisoning. Now, in the last part of the talk, I'll look at, well, how can we defend against this type of membership leakage? Like, obviously, we don't really want to deploy models where it's going to be so easy to tell whether an example was in the training set or not. And again, as I mentioned in the beginning of the talk, our concern here might not be just that someone can infer membership, but just because we know that if you can infer membership, it's very likely you can also do other things, that there's sort of other privacy leakage that might sort of pop out later, or that you might not have considered. And in a way, it's just, if you can make sure that the models you deploy are safe against membership inference attacks, you can sort of be a lot more confident that you're not going to have bad privacy issues down the road somewhere. So ultimately, we'd like to have such a defense that just sort of makes it harder to distinguish whether an example is in the training set or not. It turns out that such a defense exists and it's been known for a very long time, and it's just differential privacy. And differential privacy prevents all the attacks I've talked about today. The reason is that the sort of formal guarantee that differential privacy gives you, which is essentially that whether you've trained on one data set or a data set with one different example in it, sort of that these two worlds are going to give you essentially the same outputs. This guarantee holds for any pair of data sets and any element you're targeting. And so it doesn't matter whether the element that's being targeted is an outlier or not. It doesn't matter whether the data set is poisoned or not. If you have a differential privacy guarantee, membership inference is not going to be possible. And you can actually make this formal in that there's a very clear connection between these two things. In that if you have a differentially private algorithm with a specific epsilon bound on differential privacy, this immediately implies a bound on the ratio between an attack's true positive rate and false positive rate, between a membership inference attack's true positive rate and false positive rate. And just as an aside, I think this connection is also one of the reasons why I think it's important to look at membership inference attacks at low false positive rates, because the quantity here that we care about, or at least the quantity that is very intimately related to differential privacy, is the ratio between the true positive rate and the false positive rate. It's not their like difference. And so if you want this ratio to be high, you kind of have to go look at low false positive rates. The sort of nice corollary of this connection between membership inference attacks and differential privacy is that you can now use membership inference to audit privacy. And this has been observed in some work from my co-authors over the past few years, is that if you have a membership inference attack that achieves a certain true positive rate to false positive rate ratio, then it's not possible that your algorithm is differentially private, or at least it sets sort of a very clear lower bound on how much differential privacy you actually have. So let's see an example of how you can use this for auditing. Sort of to set the stage, we're going to look at differentially private machine learning on MNIST, sort of a very simple data set where there's been a lot of progress over the past few years. And we're going to look at a specific setting, like say models that achieve at least 90% accuracy. And over the years, there's been a lot of progress on this problem. And so like maybe 7 years ago when Chokri and Shmadikov sort of first actually tried to do this, they had sort of a kind of a proof of concept implementation of this that achieved like pretty much a meaningless privacy budget of like epsilon equal to 1,000. And then over the years, we've had sort of tighter privacy analysis, and there's been work that has showed how to use sort of better model architectures or better feature extractors to drive the epsilon, the privacy budget that you need to get 98% accuracy on MNIST sort of down to sort of single digits. And then a couple of months ago, there was a new paper that came out that was very exciting because it proposed a new algorithm and made an extremely extravagant claim that they managed to train an MNIST model to 98% accuracy with a provable differentially private bound of like epsilon equal to something like 0.08, which is like nearly sort of optimal. And it was kind of, it seemed kind of crazy that you could do this. And so with a bunch of my colleagues, we were kind of interested, well, can this claim actually be correct? And it turns out that answering such a question is not very easy, and that there's kind of 3 ways in which you can answer such a question. One is you can go and read the actual proof that's in the paper. And some of these differential privacy proofs look like this thing here. There's like a lot of math, and that's not nice. It actually turns out that in this specific case, the proof was correct. So even just checking the proof wouldn't have helped. The next thing you can do is go and look at the code. It turns out in this case, there was a mistake in the code. And so spoiler alert. And so this could have worked. But to be honest, even after we knew there was a mistake, it took us a while at staring at the code and sort of really convincing ourselves where the mistake was and whether it was really a mistake or not. And so this is also, it's difficult when it comes to implementations of differential privacy. And so a good thing to do, I think in general in these situations was to just try a membership inference attack. And here really we're going to go to sort of the extreme worst case, because again, this differential privacy bound that we saw earlier, it should hold for any data point. And so we can kind of make our life easier here in terms of the audit and just kind of go for really a worst case scenario. So the way we did this here is we constructed 2 data sets. One, which is just a standard MNIST data set called this D1. And then we created a variant of MNIST called D0, which is just the same MNIST data set, but with one additional data point, which is an adversarial example. So this is kind of really a worst case out of distribution data point. And the reason an adversarial example is kind of nice here is because it's a data point that if you don't train the model on it, it's gonna get it incredibly wrong. But if you do train on it, it's just going to learn, okay, this should actually be a 7. And so you're essentially going to have a really big gap between the model's losses on this specific example. Unless, of course, you train with differential privacy, which is supposed to prevent exactly this from happening. So now what we try to do is just train a bunch of models on either this distribution, this training set D0 or D1, and try to see whether we can distinguish them from each other. And well, we ran this attack like 100,000 times. This is kind of the bad thing with auditing at this point, is it's a kind of an expensive thing to do because you want sort of statistical validity in your results. And this is something we'd like to improve on. But essentially the gist of it is that it's actually very easy to distinguish a model that was trained on either D0 or D1, even when you trained them with this code that was supposed to be differentially private with an epsilon of 0.08. And it turns out that the distinguishability between the distributions means that it's actually impossible that epsilon in this case is lower than 2.7. And so this result actually ended up just being incorrect. And after we sort of convinced ourselves that it was indeed incorrect by doing this attack, we then went back and looked more deeply at the code and found that indeed there was a bug somewhere in how the privacy budget was used. And then we confirmed this with the authors. And so it was kind of ultimately, even though running the attack is actually fairly expensive in terms of compute, it was kind of an easy way to convince ourselves that this particular implementation of differential privacy was actually incorrect. So with this, I'll conclude this talk and just reiterate some of the main takeaways, I think, from what we've learned today. The first one, which I think is kind of the most important one here, is that measures of average case leakage are, in my opinion, not good for privacy. They're not good metrics because they don't really tell us whether any particular user is at risk. They just sort of tell us that on average, something is leaked, but that's not necessarily particularly meaningful. And on top of that, as we saw, it can actually be misleading because it might tell you that one attack is better than another when it's actually the other way around. And there's sort of a very strong attack that only works for, say, a small fraction of users, but kind of from a privacy perspective, that's a lot more worrisome. Because of this, I think that we actually will have to go back and reevaluate a lot of the things we think we know about membership inference attacks and defenses. That people have written sort of a lot of papers on sort of saying, well, this thing works for membership inference, or if you use, I don't know, dropout or early stopping or this kind of defense, membership inference is prevented. But kind of all this literature use these kind of average case metrics. And so I think it's worthwhile sort of going back and seeing if these results actually still hold if we look at sort of better ways of measuring privacy. Then we saw that if we can poison a data set, then all of a sudden privacy of all users can be at risk, and that sort of even if your data is very inconspicuous, you can still sort of force a model to memorize it if you're being the target of a poisoning attack. And then finally, going sort of even further into worst case territory, we saw that we can use membership inference attacks to get quite tight bounds on the differential privacy of a training procedure, and that this can be a sort of a useful tool for auditing implementations and catching bugs in them. Yeah, so that's it from me. Thanks everyone for your attention. I'm very happy to take any questions.
Thank you, Florian. Thank you very much. And let's go with this virtual clap round of applause. Unfortunately, this is what we get, virtual conferences or virtual talks. But I guess, personally, I truly like, all the different aspects of the talk and the research and how these are connected one to another. So this is absolutely amazing. Let me just go very quickly on the YouTube stream to see whether there is any question.